Hello, everyone. First, I'd like to thank Professor Simran Singh, who is the organizer of this session, to present the work here on digital predistortion algorithm of advanced coherent modulation schemes enabling radio over fiber for access networks. My name is Ahmad Atieh, and my collaborators from Calgary University, Mahmoud Nwayer, Muhammad Halwani, and Fahad Ghanouchi. In this presentation, I'm going to be talking about radio over fiber optical systems and OFDM implementation, then 5G of front haul, as well as digital linearization of modulated signals, then show experiments and results, as well as simulations. This chart here, which created by Nokia and Orange, shows the different services which can be served by the new radio systems, 5Gs and 6G. And this includes almost everything from autonomous cars, safety, health, as well as gaming, and everywhere in the field. The enabling technologies for the new radio are radio over fiber, the OFDM modulation, orthogonal frequency division multiplexing modulation, as well as the advanced modulation such as 64 QAM, 256 QAM, and then the signal processing algorithms. And one of them is the digital predistortion, which is going to be concentrated on in this presentation. Now, for radio over fiber optical systems, the laser light is modulated with an RF signal, and the RF signal here, it's basically will be, they give you two tones or multi-tones, and these tones will be modulated with the data signals and transmitted over a fiber or over wirelessly. So the application is going to be for wireless communication, satellite communication, cable TV as well. As I mentioned, the radio over fiber signal can be transmitted either wirelessly or over a fiber, let's say from the central office to the remote radio head. The modulation schemes is typically, as mentioned earlier, is the 64 QAM OFDM and 256 QAM OFDM. The bandwidth of the signals, the subcarriers, is typically around 20 megahertz and modulated over a carrier of 30 gigahertz RF carrier to enable the 5G wireless communication. In this chart here, it's basically the block diagram of an radio over fiber OFDM system, where you have the first block here is the RF OFDM transmitter, where you have basically the data is modulated with the QAM, as well as carried over the orthogonal frequency division subcarriers of the orthogonal frequency division multiplexing. And then basically this block is the conversion from the radio frequency range to optical signal, and using the modulation of the laser, and then the light is carried over the fiber and amplified to compensate for the losses in the system. And then eventually you have the down conversion from optical signal to RF signal, and the detection could be coherent or could be direct detection. He's going to talk about it in this presentation. Then at the end, we're going to have the receiver block, which basically deals with the RF or OFDM signal, doing the detection of the different subcarriers, as well as the modulation of the QAM signal. Okay, so the first part here is about talking about the intensity modulation direct detection of OFDM. And as you know, is the electrical OFDM signal, typically it's bipolar and complex. However, to be able to transmit it over the fiber and using intensity modulation, then the light has to be basically, because its intensity, it is only real, and it's because it is the light cannot be, the signal cannot be negative. So that's an issue. And to overcome, there is different schemes being used for OFDM. One of them is called asymmetrically clipped optical OFDM, and then this part, the OFDM signal is clipped at 0, so the negative part is eliminated, and only the odd subcarriers being used for transmitting the data. Now, this scheme is bandwidth inefficient, as you see, because I'm not using the even subcarriers. Now, another scheme is called DC biased optical OFDM, and in this scheme, the even and odd subcarriers are being used, so this is bandwidth efficient. However, there is a DC bias added to the OFDM signal to allow it become positive, and then there is a problem then here with the power. So this is power inefficient. Now, a solution for that is a combined solution, which takes care of the even and odd subcarriers, where the odd subcarriers are used asymmetrically clipped optical OFDM, and the even subcarriers are using the DC biased optical OFDM. And with this way, you will be able to send both of them and enable power efficient as well as bandwidth efficient systems. Now, there is different modification of these schemes. One of them is called spectrally factorized optical OFDM, which is improving the power compared to asymmetric by about 0.5. And there is another scheme called noise cancellation method. And in this scheme, there is about 3 dB power achievement compared to the asymmetrical clipped optical OFDM. And then there's another scheme called diversity combined asymmetrical OFDM. Now, in all of these schemes, they're trying to improve the system performance and so on. Now, in this part here, I'm going to talk about the coherent optical OFDM, where basically the detection scheme enables the system to be more resilient to chromatic dispersion and polarization mode dispersion. And this scheme also uses advanced and efficient FFT algorithms and inverse FFT algorithms to compete the nonlinearity in the system, mainly because of cell phase modulation and phase noise. This coherent detection system of the M system is being used mainly for long-haul communication and for very high data rates above 100 gigabit per second. Now, this is also used for dynamic reconfigurable networks where they need fast link setups. It's used also in data centers for high-speed interconnect. The main advantage of OFDM is because of the large number of orthogonal subcarriers. It makes them resilient to fading, to interference, to multipath. And because will enable a high spectral efficiency. Now, because of the large number of subcarriers, each subcarriers will carry a lower bit or baud rate, and that will make it more resistant to ISI for the channel dispersion. Also, the OFDM uses single tab equalizer, which is very simple. And then they are also power efficient compared to an off-keying as well as pulse position modulation schemes. The main disadvantage of the OFDM is the OFDM signal exhibits a high peak power to average power ratio, and that could put a constraint on the system to make it either operation in the linearity, and if it is not working in linearity, then there would be an intermodulation distortion causing interference between the subcarriers, and thus like the system performance degrades. Now, also another issue is these OFDM signals is they are sensitive to carrier offset and drifts. In these few slides, I'm going to show you different simulations for the direct detection and coherent detection of the systems, and using commercial software from Optiwave. It's called OptiSystem. In this software, the first simulation here showing 64 QAM of the M system using 512 subcarriers, and the data, the bit rate in the system is 6 gigabit per second. As you can see here, the signal is using the bit BERT test, generates the bits, and then carried over, modulated with the QAM signal over 6 bits, every 6 bits bare symbol, and then this data is modulated data is carried over the subcarriers, and then carried over a 30 gigahertz RF signal, and then modulated with the laser, amplified and transmitted over the fiber, and then detected here in this scenario is direct detection, and then demodulation, and then the OFDM signal is, and the QAM signal is the detected, demodulated, and then the bits are compared. This is the constellation of the system. In this scenario, there is about 6.7% AVM, error vector magnitude. Now, if I reduce the bitrate to about 1.2 gigabit per second in the system and carry it over 1024 subcarriers, the AVM improves. As you can see, the constellation is better, about 4.5% EVM. Now, in coherent example here, 64 QAM also as well scheme used for modulation, used 80 subcarriers, 60 gigabit per second. And you can see also here the system is able to transmit with about 6.4 EVM percentage for the EVM for the constellation. Okay, now in this part here, I'm going to talk about the cloud radio access network implementation, and using, this is the block diagram of the front hull of the system, the 5G system, where in the baseband unit there is the laser. And as you can see here, these two modulators. The first one is used to modulate the laser with the local oscillator to create the RF signals, the RF tones across the optical carrier. And then these tones are being modulated with the data. Then the signal is amplified, and then there's a optical bandpass filter here just to eliminate as much as possible from ASC from the signal. And then the signal is transmitted over the fiber to the remote radio head. And in remote radio head, you have the photo detector, and then filter, electrical filter, and the power amplifier. And then the signal is transmitted over wirelessly over this carrier around the 30 gigahertz. Now, typically, the parameters for these signals is you can use for signals for the subcarriers with bandwidth around 20 megahertz. And in the experiments being done in this work, it used 24 gigahertz instead of 30 gigahertz for the signal, just because of limitation of equipment. However, the simulation showed that it can be working at 30 gigahertz without any issue. And 64 QAM as well as 256 QAM of the OFDM signals has been used in the experiments and the simulations. The system is being linearized using the digital predistortion algorithm, and the system was tested before linear and nonlinear cases. Okay. Now, this is the structure of the digital predistortion system, where the samples comes into the predistorter and they create the distorted samples here and passing through the system, which is a nonlinear radio over fiber system, including the amplifier and the fiber and everything. And then the system here, this received samples. In principle, if the system is linear, these samples supposed to be equals to the gain times the x of n. However, if the system is nonlinear, then this signal would be a function of the distorted samples. Now, the distortion algorithm being used is called memory polynomial model, and it's applied in which is typically used in any optical or electrical transmitters for compensation of nonlinear distortion. Okay, this part here is the filter detected output power, which is at the remote radio head. It's you can see there's different frequency component in it, and the data would be existing in the system here at different frequencies. One of them is at 2 gigahertz, and the other one is at 20 gigahertz, and the third one is at 24 gigahertz. So with the filter, and we can use the like the mixing and create the 24 gigahertz and transmit it in the experiment here over the antenna. Now, this part here, it shows you the original signal, which is a 2 gigahertz input signal. And because of the nonlinearity of the system, you're gonna see the spectral regrowth around signal and causing the distortion in the system because of the nonlinearity. So this is something which you're gonna be concentrated on it in this part of the presentation. Okay, in this setup here is the general experimental block diagram where you have the laser at 193.18 terahertz, and this is the first modulator which modulates with the local oscillator at 11 gigahertz. You can create 2 tones from the carrier. The modulator also biased in such a way that at minimum points to suppress the DC, the carrier, optical carrier. And then after that, these tones are modulated, each one of them, as you can see here, with the data. The data is signal is 20 megahertz and then up converted to 2 gigahertz. And then the optical signal here is going to be amplified using an EDFA and then transmitted over the fiber. There is a filter 1 nanometer, as mentioned, to get rid of the ASE in the signal as much as possible, and then detected at the 40 gigahertz. And the 40 gigahertz is the, as you can see, there is different components, one at 2 gigahertz and one at 20 gigahertz and one at 24 gigahertz. So the 24 gigahertz would be basically transmitted through the antenna. This is the picture of the experimental setup showing all the components. And these 2 traces here of the OSA is the first one is showing the optical carrier suppressed and the 2 tones around it, the RF 2 tones, radio over fiber signals. And this is after modulating with the data. The parameters of the laser has a line width of 200 kilohertz and the power of 35 milliwatt. The local oscillator frequency is 11 gigahertz, and the modulation is done with 64 QAM OFDM or 256 QAM OFDM, and the signal, as I said, is 20 megahertz. The fiber is about 12 kilometers of SMF 28 fiber. Okay. The detected signal is 24 gigahertz, as mentioned, and because of limitation of equipment. Now, this is the experimental results showing this is the detected power spectra of the signal after without using the digital predistortion, and you can see that this is the growth because of the nonlinearity. But you suppress this growth once you use digital predistortion scheme, and that the constellation without the digital predistortion and with digital predistortion, you can see how much improvement in the constellation occurring. Now, this is another experiment done with the 3 subcarriers here. Each one of these 20 megahertz, so the total is 60 megahertz, and this is the constellation also as well. Now, a limit which is set by the European Telecommunication Standard Institute for the 64 QAM is 9% AVM, and for 256 QAM is 4.5% AVM. Now, as you can see here, for the 64 QAM without predistortion, digital predistortion, this is the measurements for 20 megahertz bandwidth and 60 megahertz 3 channels and 5 channels, and always, as you can see, the results of the EVM with predistortion for 64 is always less lower than the 4.5, as you can see here, percent. Now, this part here showing the experimental, the simulation part of the experiment representation and the demonstration using 30 gigahertz carrier. Now, the issue is, as you can see here, this is the laser, and the first modulator modulated with the sinusoidal signal at 11 gigahertz. So you create 2 tones, as you can see here, and the modulator is set to suppress the optical carrier. Now, after the data is passed, which is this is the bit rate, this is the bits, and this is the QAM modulator, and this is OFDM. Now the signal, once is converted up to 2 gigahertz, is modulated with the light here. So each tone of the radio over fiber signal is going to be carrying the data, and you can see here it is the first tone at 11 gigahertz away from the carrier, and the minus 11 gigahertz away from the carrier, carrying the data. And now optical signal is transmitted over the fiber and amplified. Here in this configuration, we use kind of pre-amplifier representation and then detected. Now at the output of the detector, there's the beating happening, and then this is the spectrum, and this is the spectrum. You can see the data, as I mentioned, it exists at 24 gigahertz, at 20 gigahertz, and at 2 gigahertz. And if you zoom on this signal here, as you can see, the 24 gigahertz spectra, and with the growth of because of the nonlinearity in the system. Now, this chart here, just to compare between the experiments and between the simulations, and very good match between both of them. In this slide here, I'll show you the simulation and the constellation measured at the OFDM output, and you can see the I is in, as shown here, and the about 6.7% AVM is measured. This is a summary of what has been done in this part of the presentation to represent the 5G front haul and the different signals, 21 channel, 3 channels, and 5 channels with bandwidth are transmitted and detected at 24 gigahertz and linearized because of using digital predistortion. That's the transmission over, and then the simulation. Now, in this part of the presentation, I'm going to talk about using a broadband radio over fiber downlink. Now, the issue is here is if you use if the signal has wide bandwidth, then the digital predistortion may be not efficient, as we're going to show you. But another scheme, which is distributed digital predistortion, would be more efficient. And as you can see, once the bandwidth of this signal exceeds about 1/5 of the sampling rate of the digital to analog converter, then the problem is there would be the leakage happening to the next subcarriers. So even the regular memory polynomial model is not working properly. So once you use the distributed digital predistortion, you can suppress the leakage here. The distributed digital predistortion model combined with dynamic model and static nonlinear predistorter. And this is the equations for this is the regular memory polynomial, and then the other scheme for the static predistorter. This is the experimental setup used to verify the concept. And as you can see here is the effect of the channels when then you don't use using only the red one here, using only the memory polynomial. But if you use the distributed distortion, you can see how the suppression is going down to almost nothing there. Okay, now this chart here shows you the advantage of using distributed digital predistortion, and you can see that the sampling rate of the digital to analog converter is going to be dropped down dramatically. Like for example, at 300 megahertz bandwidth of the signal, the sampling rate goes from 1500 megahertz down to 500 megahertz. So it's about 1/3 of the required sampling rate is needed when you use this digital distortion, distributed distortion, predistortion, and then that would, in principle, reflect on cost and complexity of the system. Okay, now in terms of in this part here, I'm going to present radio over fiber over space system transceiver, where a downlink and uplink signals has been transmitted using the same channel and using the same laser. So the issue here is the laser, which is on the baseband unit, first step is creating the RF tones, and then after that amplify these tones. And using a beam splitter, we create the X polarization and Y polarization. The X polarization carries the downlink data, and the Y polarization is combined and transmitted through, as you see here, a circulator through free space into the remote radio head. And in the remote radio head, you have a polarization control first to adjust the polarization and maximize the positions to original positions, and then the X polarization is detected and transmitted through the antenna wirelessly, and then a detected signal here is added as interference here, as you can see, and this signal is modulating the Y polarization of the light. and the Y polarization basically is transmitted over this using the circulator again into the free space and detected by the system at the baseband. Now, this way enables the bidirectional full duplex system, and then you have we create a predistortion at the downlink and post distortion at the uplink. This is a diagram shows the concept of the predistorter for the downlink and the post distortion for the uplink, and then with the interference, as you can see, eventually you're gonna get the original signal. And this is the measurements, experimental measurements. And the main issue here, as you can see, is the improvement of the signal to noise ratio. So if you can see the signal to noise ratio for received power, and you can see there's a huge improvement when the power is high, as you can see in this scenario. So beyond, like once you start the improvement around 36 dBm, but once you reach, let's say, minus 28 dBm is about 2, 4, 6, about 8 dB improvement in terms of signal to noise ratio. Okay, now this is a summary of what's been done in this part. Next part is going to talk about the calibration process on demand of the radio over fiber system. And the process is done this way. So using almost a similar scheme before, using single laser and using the X and Y polarization. The X polarization typically used for carrying the data, the Y polarization used to carry the a feedback signal, which is used for the calibration process. So this is the general system. As you can see here, the signal is transmitted, the X polarization is transmitted through the antenna, and at the same time it's tabbed and modulated here, and then transmitted again and detected the feedback signal, the modulation, and create this signal here, Y prime. And this Y prime is used for the predistortion system to compensate for the distortion in the system. So this is kind of the system calibration process. So where you have no signal on the X polarization and the Y polarization would be modulated with the signal. And you can see here, for example, if you look at point K in the system, at here you have the laser and then the two polarization X and Y at point L, and at point L prime here, you see still the same thing, but because of the attenuation, you can see the signal level goes down. The point M here is the Y polarization, which we can carry the data on it. So this is the data called the feedback frequency. And then eventually you're gonna transmit this data over, after modulation, you have the two signals, and then eventually you're gonna get this signal detected at the baseband unit. Now, the process of calibration, as you can see here, you have the training process where you have the observation path training. You send a signal, and then using the observation path, now this signal is around 200 megahertz used for feedback, and this is the distortion. Once you apply post distortion, you get it back, and then the parameters here used for the downlink signal as well, and this process is used to the feedback signal is used to calibrate the signal transmitted over the radio over fiber with the downlink data. This is a summary of the experiment. And as you can see here is the original signal, which is the black, the original signal is the blue one here. And then after the signal with and without digital predistortion and feedback. Now, if you use with feedback signal, as you can see here, for a signal of 40 megahertz bandwidth, you can see the improvement is about from -30, the adjacent channel leakage from -31 to -44, and the EVM from 7 to 4 drop down, and the normalized maximum mean square error is going from -6 to -24, which is -7, which is a huge improvement. So this is kind of scheme. If you use the active calibration observation path in your system, you can achieve much better performance in the overall system. Okay, so with this, Basically, this is the reference used in the work, and the paper is open basically for answering the questions. If you have any questions, thank you very much.